All right, welcome to Physics 30. I have a question here that is about three forces on a ball. There's three forces here, one, 2, and 3, and I've written on them 2.4 newtons, 1.5 newtons, 1.3 newtons, and the corresponding angles. So this first one is 16 degrees from this, again, it's from this line here, this kind of x-axis or the east-west line. This one's 9 degrees, it's straight up. And this one is 186 degrees from this line. So those will become useful very soon. The reason I wanted to make this video is to show you how to add three or more vectors together, calculating it. I think you're going to find there's quite a powerful method here. It can even be used for two, although with two often you can use if it's a right angle triangle, you can use that, or if it's a different kind of triangle, you can use that. So that for two, there's other methods that maybe you might think are easier, but this method also is good for that as well. So first I want to do a little introduction about what basically the theory behind this method, and then we'll try it on this example question. So the first thing is we're going to actually convert each one of these vectors, these force vectors on this ball, into their x and y, so the x and y components. So I'm just going to draw this force vector here. So if this is the, this will be, see how well I can do here. If this is the grid and this is the vector here, okay, there's going to be a, so we're going to just call this f. There is going to be an x and a y component to it. So in red, I think I'll just write down here. There's an f component, or sorry, an f of x, f, and we use subscript x. That just means in the x direction. In a Cartesian plane, you have x and y, right? So, and then the other one would be the y. So I'll do that in green. Okay, so this here, this would be f of y. Hopefully you can still see that. That green was a bad choice, I think. Anyway, so making up this force vector, we can break it down into f of x and f of y. And then there is a third, or another thing, and I'm going to actually put it in blue. Should I put in blue? Maybe a light blue. And that is theta in here. So that's the angle theta. Another terrible choice. You can barely see that. Okay, so you have theta and you have f, and so maybe I'll write that in blue. There's two different, there's rectangular form and then there's polar form. So for polar form, you are given things with a magnitude like f, and you're also given theta. So you have f and you have theta to think about. That's magnitude and direction. But you can also write this in a rectangular form. Rectangular form. It's F-O-R-M. Oh, I just destroyed that. Okay, let me try. Rectangular form. And in rectangular form, you have f of x and you have f of y. Okay, that's an x there. And so I'm going to show you how to go back and forth from one another. And essentially, these are all polar form forces, or given in polar form with a magnitude and direction. And we're going to convert them all into rectangular form, and then add them all up, and then convert the sum back to polar form, and then we'll have our resulting force on this ball. Now we expect, just looking at the forces, that it's going to be, if we add it up graphically, that we would have this, then we go up, and then we come back down. So we're expecting a resulting force vector that goes from here, and it goes maybe, I don't know if it'll be 45 degrees, but it'll be a little bit let's say around 45 degrees, and maybe around, I don't know, it could be around, looks like about 1.5 newtons. So anyway, that's kind of what we're anticipating. So let's see what we can do here. So we make this amazing table. I'm going to actually just use this. I'm going black here. And the table sets everything up hopefully fairly beautifully. We have f, and then we have theta. Okay, and I'm spacing them out. And then over here we're going to convert things to f of x and f of y. And I'm also going to write the equations for these in just a second, and now I'm regretting how close this is. I'm just going to move it over a little bit. So we're going to go to f of y over here. I know I didn't move it much, but okay. So so first of all, we're given everything in f. So I'm going to write down the three vectors, and the first one here is the 2.4. So and actually I'm going to try to put this in. So 2.4 newtons, and theta is 16 degrees. And the second one is 1.5 newtons, and it is at 90 degrees. And the next one is 1.3 newtons, and it is at 186 degrees. Okay, and so we're actually going to convert each one of these into its into its polar form, or sorry, rectangular form. It's already in polar form, and let's see what we get. So how do we convert it to f of x? Now here is where we actually are going to use the right angle rule of SOHCAHTOA here. So if you remember, SOHCAHTOA, if in this case we want to find out what f of x is, and we know f and theta, how do we solve for f of x? Well, this is the adjacent to the angle, and this is a hypotenuse. And so we look at these, we're going to use the cosine essentially. So we can say f of x, or actually let's do it in a couple steps. Cosine of theta. I really am getting distracted by sloppy handwriting here. I wish I could. Anyway, here we go. The cosine of theta is equal to adjacent over hypotenuse. So that is f of x over f. Okay, and we're trying to find theta, or sorry, we're trying to find f of x. So we multiply both sides by f, and so f cos of theta is equal to f of x. Or we can say up here, switch, we can say f of x equals f cos theta. So that's how we're going to calculate f of x. We're going to take the force, the magnitude, times it by the cosine of 16, and that's going to give us f of x. Okay, and then f of y, how do we find f of y? F of y is the opposite. Okay, we don't have the adjacent this time, so now we're going to use the sine. So the sine of theta is equal to the opposite, f of y, over f, and so therefore f sine theta is equal to f of y. So over here we can say equals f sine theta. That will be the equation we'll use. Okay, and then now we just simply do the calculations, and I didn't do the calculations beforehand, so I'll just do them quickly here. It shouldn't take very long. So the cosine of theta is 16 degrees times 2.4, and again here you want to probably leave as many digits as you can in this part, but when we come back to the final answer we're going to have to only have 2 digits, okay, for each one. So I'm just going to write in 2.307. I think I'll just do that many digits for now. There are more digits I could put in there, and then f sine of theta. So then I go sine 16, and then I'm multiplying by 2.4. That gives you 0.6615. Okay, and we're going to do that for the rest of them as well here. So cosine of 90, that is 0. So 0 times 1.5, and you might be wondering, why is f of x for this vector here 0? Well, look, there's no x component. It's all y component. So cosine of 90 will be 1. 1 times 1.5 is just 1.5. Okay. Oh, and these units are all in newtons here, so I'll just put an n by them. Even the 0 newtons. And then 186. Now I'm expecting this one here, this f of x, to actually be a negative number because f of x is negative and f of y is negative. So depending where the vector is and which coordinate will depend on its sign, but the calculator should figure that out automatically. So if I go cosine of 186, I should get a negative number, and indeed I do. 186, I don't think that's 186. Let me change that because that's not 186 at all. That's I think that was 46 more, yeah. So this should be 180, it should be 226. So let me just erase this. Let me erase that. That was close call right there. Don't want to have things wrong here. 180 plus 40 is 220. 226, because it's 46 degrees beyond that one. Okay. So let's erase it here. It's 2. Oh my goodness, I erased the other number. Okay, so this is 226. Okay, disaster averted. Let's continue on. So we have the cosine of 226. Yeah, that's good. That's negative 0.69746, and I'm going to times that by 1.3. So we get a negative, the negative is important to keep there, negative 903, let's leave it at that, newtons. And I wish I was better at the penmanship part of this here. And then we have the sine of 226 times 1.3, okay, and we have a negative 0.935. I'll put the 1 there too. Okay. All right. So we have these. We have f and x for both, or for all three of the vectors. Now we're going to actually end up adding them all together. Okay. And so if there's a minus sign, we subtract instead of add. But we add all the x terms, the f of x terms together, we add all the f of y terms, we're going to have an f x total, f of y total here. So it's 2.307 plus nothing minus 0.903. So that gives you 1.404. It's a positive value. And then this one here, this is 0.6615 plus 1.5 minus 0.9351. Okay, so this gives us 1.2264. So again, this is, you can call this one x of x total, and this is f of y total. Okay, or anyway, it's the sum of all these f of x. And now we're going to go actually back the other way, okay, and we're going to convert it into polar form, so that we want to know, this is nice, they having the x and y components, but we want to know what the total force is and what direction it is. And so we're actually going to go in the reverse direction. And so if we go back to this little diagram here, hopefully you can see this diagram, it's not too bad. If we know f of x and f of y, but we're trying to find force, this f here, so we have x of x and f of y, and this is a right angle triangle. This is a right angle triangle here. The question is, how do you solve for f? Well, f actually ends up equal, I'll put it here actually, well, this is the same thing as a c squared equals a squared plus b squared. So it'd be f squared is equal to f of x squared plus f of y squared. And therefore f is equal to the square root of f of x squared plus f of y squared. And now theta, this is an f by the way. Theta, now what does that equal with respect to these two? Well, this is opposite of adjacent, so we'll be using the tan, and I'll just use a different color pen just so I don't get confused. So the tan of theta is equal to the opposite over adjacent. So the tan of, again, theta is what we're looking for, is f of y over f of x. And so actually theta ends up equaling the inverse tan. So we take the inverse tan of both sides of f of y over f of x. Okay, that's f of x there. So these equations should look a little bit familiar if you look at the the question sheet. You'll notice that all three of these are on there. This is where they come from. They come from this triangle, this analysis of going from polar to rectangular form and back and forth. And so now we have an equations to use when we have f of x and f of y to get the f value, the original or the final force vector. So I'm going to just put that in here in my calculator. I'm going to take the square root of 1.404 squared plus 1.2264 squared, and that gives me 1.8642 newtons. These should also be newtons. But I can only have two significant digits here, so it's 1.9. Same thing as 1.9 newtons, or it rounds up to that anyway. And the theta here is, again, we use the tan inverse of f of y, which is this term, over f of x. And so let me do that. F of y is 1.2264 divided by 1.404. Okay, I'm going to take the tan inverse of that. Okay, and we get 41.137 degrees, which is rounded to 41 degrees. And so you can see that's what we were thinking before, is around 1.5 at 45 degrees. Well, yeah, 1.9 at 41 degrees. So it's coming out here. Okay, and that's, yeah, this is your F. This would be called your F total, and this would be called your, I guess, theta. Yeah, I guess we can call this F total, or resultant, I guess. Anyway, it's fine. Just it's your final resultant total force on the ball. Okay, so that's a big method. It took me almost 20 minutes to go through and explain that. But this method is very powerful. This we use 3. We could have cut it down to 2. If we did 2, we'd only have 2 over here, 2 f of x's and 2 f of y's. Add those up together. That would have gotten, we've been able to do it. We could do 100. So you can see how this is so powerful. You can see why something like these equations would be used in a program, like in a video game or something like that. We could use these equations to add vectors together if we needed to. And we can add as many vectors as we want. So we have a video game that has a character jumping through the air, and so there's gravity, and there's a fan, and there's another force on it, and maybe 2 fans, and it's going through. You could actually calculate the force on it. You could also do it a different way, so you don't necessarily have to use this, but this is a powerful method. So I hope you understood it. Please, if you have any questions about this method, or if you saw that I did a big mistake anywhere, let me know. Otherwise, hopefully you can finish all the vector questions. Good luck. We'll talk to you later.